Well, everyone online, you just missed the intro spiel. The very condensed version is, hi, I do scientific machine learning, and I'm here to talk about software that does scientific machine learning. So cool. Let's crack on. So, introduction to the JAX scientific ecosystem. First of all, just like a quick show of hands. Who's used JAX before? Who's sort of familiar with this? Just like I'm seeing, okay, decent number of people. And then likewise, the rest of you maybe like PyTorch or something like that, I'm guessing. I'm seeing lots of nodding of heads. And I got told to expect one or two Julie people hiding in the corner somewhere. Might be one of you two guys. Okay, well, it's no one's perfect. In that case, I probably won't try to motivate the sort of why Python side of the story, which I think sounds like you guys are already on board with. I know that a lot of people are still using older Fortran code and stuff like that, and I won't try going there. I've seen laughs and a few shivers. Yes. It's great to be in the future, isn't it? So, I do one slide of intro worth to JAX. Is it worth me doing this? Or is this, I'm seeing nods. Okay, sure, let's do this. Okay, so an introduction to JAX. So part one of the story today is going to be this quick recap, one slide recap of JAX. Part two will be then where I say something about using a lot of the software tooling for deep learning, kind of with a view towards, non-specifically scientific kind of stuff. And then part three, I'm really going to talk about science in particular. And I do have a special treat to do with black holes for you at the end. I know my audience. So part one, JAX recap. What is JAX? So JAX, first of all, it's this sort of, hopefully vaguely familiar if you're coming from NumPy, vaguely familiar looking API where it just kind of looks like Python functions like normal. So here, I've got a few inputs. I've not really told you what they are, but I can call them just like I can call anything else in Python. And then in particular, where normally you might be used to write something like numpy.sum, np.sum. Then here we are writing jnp.sum, and it's basically the exact same API. It's just JAX's own implementation of that exact same API standard. And so the goal here really is that this should just feel familiar and it could be a thing that you're used to working with. Now that's kind of neat, but why bother implementing this? And what is it that makes JAX JAX? And it's really this second thing, is these transformations. And so these are these extra function to function transformations that we stack on top, usually as decorators, we stack on top of our function. And so if I look at what I've got here, I've got compute loss. This is the function, right? I pass in some models and data, and the thing I get out is a loss. Then I stack on just the JAX.grad. Forget about the JIT for a second. Stack on just the JAX.grad. And what I now have is a new function where what it will do is it will compute the gradient with respect to the first argument of the output with respect to the first argument. So compute loss gave me the loss, and now grad compute loss gives me the loss demodel. That is to say, the parameters of my model. And so this is something where if you're coming from PyTorch, you're used to like building up these computation graphs, they're doing like dot backward, and you have these like dynamically built computation graphs that sort of like store this like state as they get built. JAX is a slightly different model. I think certainly one that I prefer slightly. It's sort of more functional programming in that I've started with a function, I project it down, I have a new function, this function computes something else, it computes the gradient instead. And then what do I have on top of that? I've got JAX.jit, and so this is another function-to-function transformation where the function that's going in is my grad compute loss, and the function that's going out is this JIT compiled version of that, which has then been lowered down and compiled. And so actually what you'll find is that the first time you run this, the Python code is traced and evaluated, and all the operations inside are sort of stored, and the computation graph is built up. And then that computation graph is passed to the back end, JIT compiled into, so you could sort of think this is a little bit like compiling C or CUDA or something like this. And then every subsequent invocation will just hit that compiled version of the code. And actually, as a result, your Python code don't actually run once, just to grab the computation graph out of it. And so what this means basically is that things go really, really fast. And this is, by the way, super useful. Okay, one sec. This is super useful for these kinds of scientific applications, where in something like big deep learning models, where you've got big stacks of layers, the overhead of Python often doesn't matter that much. You're mostly dominated by these gigantic macros happening on a GPU. That's kind of most of your time spent. But a lot of scientific models are more itty-bitty, solve a differential equation, this kind of stuff. And in this case, the Python overhead can really dominate. And so JAX's JIT compiler is a huge boon for models of this type. Yes, go for a question.
How does JAX's JIT handle the dynamic typing in Python? The most JIT I know of, sort of leverages the fact that you actually type your functions. There's no typing in that function.
Yeah, you don't need that.
So is it just on first run, and then if you run it again with a different type, then it has to then do another JIT run?
Yes, this exactly. Yes, exactly. So it will specialize based on the shape and the D type of any arrays you pass in, and everything else just based on like that identity, the EC and the hash. of that. And then for any set of things matching that specification, there will be a JIT compile version of that permission. Yeah, and it's a tracing JIT compiler, if that's going to be asking for. Yeah.
Sure.
Cool. Which note, by the way, guys, please keep jumping in, ask questions anytime you like. Right. So far, so clear. Wonderful stuff. Seeing people nodding. Let's move on. What's next? So, well, anyway, this is another nice thing. I think admittedly fairly standard these days, but the same code runs on both a CPU and a GPU. So, prototype on your laptop, run it on your cluster. This is pretty useful. So we can just run this thing. The thing I do quite like about this is how easy Jack makes this and how there's some cool stuff happening here under the hood. Where if I write just compute loss, I don't know if you can see, maybe I need to step out of the way. Compute loss, okay, great. I'm just like running some my laptop CPU or something. And now let's suppose I want to run this on a cluster of 32 GPUs. Well, what do? Is I say, here's my data, please split it across, this is a list of GPUs, this is just a list of 32 device objects. And I say, please split it across these GPUs. And then the model, this is going to be a replicated, so that's just saying, please pick a copy of my model at every single GPU. And ta-da, I now have data powered. So my model is now a copy of that's on every GPU, and it sees a slice of 1/32 of my data. And so this is what Jack refers to as compute follows data, where having specified where your data lives and having written this gigantic function that you sort of pretend is just, like you're just writing down mathematics, you don't have anything else. It then figures out how to compile up functions split across every individual GPU that you have in your cluster. So this is super cool.
Is it odd that the functions don't also need to be put on the devices?
No, they do not.
All devices share all global namespace.
What do you mean by global?
All functions are defined on every device.
The functions are defined in Python right here, right?
They have to go.
So do you mean the details of like sending the operations to the device and so on? Yeah. So basically, Jax takes care of all of that level of things under the hood for you. The level of abstraction I'm sort of trying to get to think about here is, where does my data live? Write down an abstract mathematical function. Everything else is done for you. If you're saying, does things have to get sent to devices to actually be run, then like, yes, of course it does, right? Yeah.
But is it sending the actual compilable function every single time, or is it sending it once and then it lives there?
Oh gosh, I think it would send it just once, to be honest. I don't see any reason why it would do otherwise. I've actually not checked that detail. This is an interesting point. Questions? Keep going. Okay, so ecosystem. So this is really the thing I'm here to talk about. This is kind of the end of my first slide. So I talked a little bit about Jax, ecosystem, and let's fill in, what does that model often look like? And so this is where we start leading into this collection of other libraries that built into Jax, and the one I'll start with is Equinox. And Equinox is a way of defining models. And so typically I say, here's my module. If you see my PyTorch syntax, it's designed to look very similar. Subclass that, here's my model. We're going to define a bunch of stuff. We'll do that dot later. But then I say, check the model, and I just call it this code, and it works.
About the existence normally are very class-based, right? But then
Sorry,
like object-oriented phase, right? Whereas Jax is functional.
yes, indeed. This is a common mistake. I'm going to use the word. Sorry. Okay, what's going on here? First of all, using classes is not object-oriented. Mutating classes is what makes it object-oriented. You can totally have a class in functional-based programming land. You just don't get to change them after you've initialized them. And this is actually what we're doing here as well. So what you actually end up with here, by the way, is you get your model object. This is some fixed, immutable thing that you never get to change after this thing. You pass it into your compute loss, and that goes away and does a bunch of like functional programming, part of mathematics. And then the thing that's going to be spat out of this is we'll call it the gradient. So that's actually going to be another copy of model, this time with the gradients applied to it. And so the output of compute loss will actually be a new object of this type with the gradients on it. And then for those of you worrying about like overheads of copying things and so on, like Jax does smart things here. So you can please say like, please reuse buffers, please don't like, duplicate memory, blah, 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 blah. So that can be made efficient too. Does that make sense?
Yeah.
Cool. Since you touched on it, by the way, this is one of the things I really like about Jax over PyTorch in distributed settings in particular, where if you've ever run with like PyTorch's like data parallel or anything like this, then it only mutates one GPU's version of the class, and the other GPU's mutations in something like a batch norm or something don't get seen actually. And this the functional programming approach, I think, really improves this. Okay, so end of this. This is the purpose of today's talk. Part 2, deep learning. So this is where I'm going to sort of speak to sort of a fairly general deep learning kind of end of things. And so the first thing, as we briefly saw just now, is Equinox. So this is a way of building these parameterized functions, right, which is what models are, right? They usually are forward pass parameterized by their parameters. So neural networks are a special case, but we'll see other things later too. Let's import a bunch of things. Let's define a linear layer, the simplest possible model we could possibly imagine, right? Deep learning 101. So I say I have a weight and I have a bias, and then I have a forward pass through that through my model. So I've just defined the call, and I say, please do a map model against weight, add on the bias. Okay, job done. This seems fairly simple, I hope. And then how do I initialize it? Okay, what's going on there? So I've said I want an inside and an outside, so those are 2 integers. And then I'm going to go ahead and I'm going to define my weight as being some normal random variable of the equivalent size, and my bias will also some normal random variable of the equivalent size. And then the only interesting detail here really is this key thing. And what's going on there is simply that if you're used to using something like PyTorch or Julia or something like this, you often just like sample randomness kind of exogenously out of thin air. And implicitly what's happening, right, is you have this like stateful pseudo-random number generator that's producing these things for you. JAX makes this pseudo-random number generator explicit. You pass around the key or the seed, how you prefer to think of it, for that generator. And then in particular, you can see what we're doing here. So we say, great, I've got one of these things, but I like 2 of them. One way waiting for my bias. And I guess that's actually a type, that should be a B key. Okay, so you've got W key, you've got B key. And so you have these 2 keys, and you can now sample randomness using each of them.
How do you pass the seed in a parallel setting?
Exactly the same way you pass any other argument. It's just
Is it a copy and then you're getting the same seed?
Oh, so typically what you would do,
You generate different key for different machines.
exactly, yes, exactly. So you do this JR.split of how many machines you have, and then each machine sees a separate key.
Sure.
Yeah. And so this sort of makes it impossible to silently get the same randomness, you know, kind of like by design, right? Yeah, yeah. Which is quite nice. This also makes reproducibility super, super cool. One of the libraries I'll briefly show later has got this wonderful example where they trained on a TPU, I think it was, for like a couple of days, and then they switched to training on a GPU for a couple of days, and then they went back and retrained that section on a TPU instead, and they get like the exact same effect across every single batch, right? And you're laughing, that's like impossible in PyTorch or something like that. You just cannot do that. I'm not here to shit on PyTorch. I do use that every day as well. But this is a thing which is super cool in this model of things where you explicitly control the randomness all the way through. So great for like resuming from preemption or anything like that if you're dealing with that too. Okay, great. So what is this thing? First of all, it's simple. It's easy to reason about. It's a data class. You're familiar with Python data classes in the standard library? People mostly nodding. Yeah, if you haven't seen that, it's basically just like a tuple, but you know, with like a class instead. So yeah, so this is a data class. This is just standard Python stuff being standard Python. And then I've used the word PyTree here. This is a JAX word. All that's really saying is that this is a class that JAX knows how to understand. When I pass it across a grad boundary or a JIT boundary or something like that, coming back to your point earlier about how does it know when to recompile? If it was just some other arbitrary Python object, it would just go ahead and just like use the identity of that object. If it's something like a tuple or a list, it will look inside of it. And these things it can look inside of are called PyTrees. And so it can look inside of these and find the weight and bias.
So what makes that a PyTree?
The fact that you subclass Equinox.module, one of the things that does for you is it tells JAX, this class is a PyTree, please look inside of me. PyTrees are isomorphic to tuples. They're just fancy tuples. It's not more complicated than that, really. Yeah, question.
I need a clarification about the key part. So were you saying that if I were to run the same code with the same key on like any device, like WP, BT, and like subdomain lines, you can be identical?
That would be the plan. That's the plan. Yeah. In practice, you'll see slight variations due to like non-associativity of floating point arithmetic and, you know, kind of crap like that, right? But like for the most part, yes, exactly. Cool.
Does JAX have version stable keys?
It does not. Yeah, that's explicitly by design. It would be too annoying for that to be the case. Okay, what else? Elegant, PyTorch-like syntax. Hopefully you look at this. I mean, everyone's used PyTorch at some point, right? It's meant to be simple. This keeping parameters and forward pass together, this is in contrast to sort of some of the functional programming stuff you were talking about earlier, where you often think about, oh, my parameters are over here in this bucket, and I pass them into a function I've defined over here, right? All I've really done is I just put, you know, I've got one bucket called linear and it holds both the forward pass and the parameters together.
That one question.
Go ahead.
I feel like that was a positive of JAX, right? So keep this thing separate. So that was like, yeah, it feels neat, right? But then all these practices try to do the PyTorch way, right?
I mean,
What's the reason?
I guess partly this is going to be a matter of taste. Like if you really like having separate functions, like free functions and parameters, like, go for it. You can do that. You probably wouldn't use Equinox, but you can do that if you want to, Jax. What's the reason for wanting this? I guess mostly just like neatness. This is just namespacing, right? Like if I wanted to, I could create a brand new Python file and say, here are my parameters, here's my function. Or I can create a brand new class and say, here are my parameters, here's my function. It's just namespacing. If you don't like it, then like it's not a big deal, really. Yeah. The only other thing I might touch on is that, like I say, this is just a namespace. There's actually nothing special about call here. I could have defined any method, and then that would just be, I could do dot whatever method. So if you have like a VAE and you're like your encoder and your decoder like separately as methods or something, you can do that. But yeah, it's not important, just namespacing. Cool. And then unforgettable. This is another thing I like to emphasize. People, particularly who've used sort of other things coming out of other ecosystems, Julia, the inheritance, the things like this just work. The goal is really for this to be a very robust kind of system. And basically every edge case you can find, we've got like a warning labeled against it somewhere. Cool. That brings us to the end of slide 1 on Equinox. Now, I do have some advanced stuff for like the programming geeks in the room. But like, oh, but what about? And I get the sense this is kind of coming out of this corner, isn't it? Let's see what you think of some of these. So, first of all, abstract stuff. Actually, coming out of Julia, you'll really like this. It's directly explicitly inspired by the Julia type system. So this is something where you I might have like a concrete model, linear MLP, whatever it is that it's doing. But very often I want to define some sort of abstract interface. Like I have a forward pass, but I'm going to try many different models over the course of my hyperparameter optimization or something. I need some kind of way of defining an interface. And so the way that we do this here is by using these abstract-based classes, where I say here is some abstract class, and this is a way of defining this interface. Every subclass must define this step method. And then maybe I define, say, another abstract subclass that fills in the step method, but now says, by the way, I like an abstract class variable. And then you define a concrete subclass of that fills in the class variable. And now you have a concrete thing you can work with. And then sort of speaking to the Julia point, once you have a concrete class, you can no longer subclass it. That's not true in Python in general, but it is true in Equinox. It's a nice programming pattern that is explicitly taken from Julia. And so this is just sort of a nice way of defining these things that makes your code fairly robust. Yes, in fact, I explicitly call this out. And then there's also the thing that I do like about this, beyond what Julia does, in contrast, I realize I'm pulling a lot on the differences here, is this defining of like interfaces, or you also hear people saying like traits and things like this, right? It's, again, we're trying to sort of do that, but more seriously. Okay, also auto-differentiation nerds. Do we have anybody who like really cares about auto-differentiation? Like some of this like weird, I've seen at least one couple nodding people. Yeah. Hey, cool. Okay, guys, do you know, first of all, treeverse, is that familiar? Treeverse, like binomial checkpointing? No? Ooh, okay, so you've heard of like gradient checkpointing, right? So you have like a loop of operations, maybe it's like multiple layers in a forward pass or multiple steps in a differential equation solve or something like this. And you say, I will place down a checkpoint every 5 steps or something, right? And then if you do this optimally, you get square root overhead. So you square root amount of memory, square root additional recomputation, and you've got some memory savings there as a result. But have you ever seen recursive checkpointing? No, okay. So the idea here now, right, is you've got a checkpoint here, you've got a checkpoint here in your unrolled loop. But during that little forward and backward pass that you do inside that little checkpointed gap, you could put more checkpoints if you wanted to, like nested inside. And it turns out if you do this correctly, so this is called binomial checkpointing or recursive checkpointing or treeverse, you actually don't get square root overhead, you get logarithmic overhead. And this is provably optimal. And so if you happen to want this is the thing we have. In fact, we go one step further. It's not only optimal with respect to a known fixed criteria, which is what you normally see in gradient checkpointing, but with respect to an unknown final step in some sort of arbitrary length while loop, as it just keeps going and going and going. And you sort of dynamically place down checkpoints in a smart way. So this is kind of cool. This is super useful, in particular for differential equation solvers, and in particular for like loops over layers in deep learning models.
Yeah. So checkpoints equal 4 mean if you're doing this recursive.
So what does that mean here? So what that means here is that I have allocated space for 4 checkpoints in memory. And then as I go through making step by step, I will fill those in and or evict one and replace it with the contents of a current step as I go through. So I have at most 4 checkpoints stored. And those are stored, in an optimal way. Yeah. So to speak to that point, I actually have a little diagram. So what's going on here? So this is saying, you know, first step, store it, second step, store it, third step, store it, fourth step, store it, fifth step, please omit that and fill this one in instead. Keep going, you end up patterns that sort of look like this. So this is pretty cool. This is super useful. And so, yeah, I've called out Treeverse here as the name. And this is, as I say, this is asymptotically optimal logarithm problems code. It's cool. Side note, anyone who's like feeling particularly masochistic, please go have a look at like the source code for this. Unironically, this is probably the single most difficult piece of code I've ever written. I say that as someone who writes like a lot of code. Please use this so you don't have to do it yourself.
That use that sort of.
Say that again.
Are there any other audited packages?
I don't know of any other implementation in Python. I think the original authors of much of this have like one or two things floating around in like C from like 3 decades ago, right? But like unless you're working with that, then no, nothing. That's I guess I don't know of any other implementation in any other modern language. Let's make that statement. Cool. Okay, so Jack's typing. So let's move on to a whole different thing. This is a whole new package. I promise you this talk will not be package after package. We have things to break it up. But what's going on with Jack's typing? So this is these compile time shape checks. So what's going on here is, how many of you have at some point in your lives written a Python function where it takes in, say, 2 arrays, and then you've written a comment that looks like this? I see smiles. Yes, laughter. Yes, we've all done this, haven't we? And then at some point, this has not been true, hasn't it? And your code has been buggy. It's been silently wrong, perhaps. Yes, we've all been there, I think. So let's try and do a little bit better. And so Jack's typing now is a library which allows us to go and fix this by saying, hey, I can now put my shape and in fact also my D type directly into the type annotation for my function. And so here I'm saying, here I want some argument of batch dimensions, and then plus also this other final dimension I'm calling dim x. And then I'm going to have another parameter y. They should have the same batch dimensions, and then some other dim y, I'll call it. And then I'm calling this thing batch outer product. So, you know, fill in an implementation, and this is what we're going to declare output to be. And if someone calls this with incorrect shapes, or if the implementation is buggy and does not produce the right output shape or D type, then errors will be thrown, and you'll be slapped over the hand and scolded for messing up. And so this is something where I'm actually supposed to be basically anyone who does any kind of Python at this point. The name is Jack's typing. That's actually kind of historical at this point. There is no Jack dependency, and it works with PyTorch and NumPy and TensorFlow and so on as well. So I think this is hopefully useful to probably everyone in this room, Julia folks included. I promise I will stop beating on Julia at some point, but this day has not occurred yet. Okay, let's do a case study. So this is coming back to this preemption and like keys reuse and things like this that we were talking about earlier, right? So Levanta, this comes with a snazzy logo. This is a framework for training foundation models written by some of the fine folks over at Stanford. And the goal here really is we want to try and train. Like seeing laughter with which bit? No?
Ideally more than 20.
I mean, I'm quoting. I did think it was a kind of funny, like discounts of up to 50% or more. That tells you nothing, right? But I'm quoting. It gives you some sense of the scale, I suppose. And so the point that they're trying to do here, this is separating the logic of the model, the scaling of the model. So the sort of the mathematics from the physical hardware that it's running on. So we define some model that we saw this earlier, something Equinox, something. I go ahead and I define some train step. And then inside of that train step, I'm going to go and compute some gradients of my loss function with respect to my model. So I'm sort of, filling in some, there's some blank spaces here, dot, 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 whatever. Okay, I have something that looks like this. And how does Levanta now fit into this? It says something like, please split up my data, split up my parameters in certain ways across my devices, split up my model as specified, split up my data as specified, and then you end up with pictures that you start drawing that look like this, where you say, oh, my model split up like this, my data split up like this, and so on. And so the goal here now is providing these easy ways that we saw a little bit like we saw earlier on my very first slide about splitting up data. And so Levanta is a library explicitly designed to make this doable, and then it adds on top things like robustness to preemption, or all this kind of useful stuff too. So this is kind of cool. This is built on top of Equinox. and is, I think, probably one of the de facto standard libraries in this space now. So we get things like this bitwise reproducibility that's coming from the use of JAX and G keys, robustness to preemption, because you can just start up again, you know, it's easy. And that's the end of our slide. So that's kind of cool. Okay, so I'm talking to Astro people. Let's do things that are maybe sort of moving towards the Astro end of the space. Let's talk more science and less deep learning. So scientific model. The first thing I have for you here is differential equations. Okay. So Diffrax. So Diffrax is our differential equation solving library in JAX. So this is a bunch of ODE and SDE solvers, also some PDE ones. And the thing that's kind of cool here, actually, as compared to something like scipy, is that scipy was written in a pre-autodifferentiable world. But we're there now, and actually we can redesign our APIs to do much stronger things, much better things. So we'll see that very briefly here too. So from Diffrax, import a bunch of stuff. Differential equation solves. We're going to solve an ODE. The solver we're going to use is this simple Inferno 5. I don't know if people know this one is a stiff differential equation solver, but so import JAX, define some ODE, define my solver, and notably something in all of this. I've written down my ODE. I'm not sure what it is, but I've written some vector field describing the right-hand side, dy dt equals blah blah blah. And then I've written down my solver, and I'm not going to tell you the Jacobian of my vector field, which is the kind of thing that normally appears in these implicit solvers, where you need to start doing like Newton root finds in order to solve your differential equation. And the reason I don't have to do that, right, is because I can do, you know, jax.rad and get the Jacobian of my vector field for free. And it's nice how, as a result of this, you sort of start working through the details, and your whole API ends up being much beautifully cleaner than you'll see in something like scipy. So I define some initial condition, and then I say, please solve my differential equation, some ODE, using this solver, this interval, this time step, this initial condition. And then, you know, like you get options, you know, color, dot, things, there's like 20 different more options for customizing every damn thing you might wish that should change. The quick sort of aside for the numerical differential equation people in the room, if there's any here. The fact about ODE term is kind of an interesting point here, because what I'm saying here is that I'm doing dy equals some vector field dt. And if I was doing something like an SDE, right, I would want dy equals some vector field dt plus some other vector field d Brownian motion, right? And actually, there's some new numerics that went into all of this to make that work, where the fact that I'm in ODE term is just specifying a dt, but I could have written a different term there that specifies dw, or I could have done d forcing function, d control, d something. And from the solver's point of view, it does not care. The exact same differential equation solver can be used regardless of whether or not it's an ODE or an SDE or something like that. And this is something new in the world of numerical differential equations, where typically someone says straight from the get-go, I have an ODE, I have an SDE, and now here is my class of allowable solvers. But we actually have this ability to go ahead and reuse the same implementation of the solver in multiple ways. And that extends beyond just solvers. This extends to things like you have an event and you want to terminate your solve early, or you want to differentiate through your solve. Like all of the things you could possibly wish to do can be applied to every part of the thing, regardless whether it's an ODE or an SDE. So the code here is actually very concise as compared to any other implementation.
Is that by doing this nested class typing, or how are you doing that?
How are we doing that? I mean, I guess the sort of the abstract stuff kind of comes into it as part of like a convenient way of describing it. I wouldn't describe that as necessary for the numerics, right? And then as for how you're doing this, so a term object, one of these things, has a few different methods. It has a vector field, so please evaluate. So if you have like dy equals f dt, there's please evaluate f. There's please evaluate dt over some interval. There's please multiply these two things together. So you've got these three different things. So f, the control, and multiply the two together. So that's in general, that can be any bilinear operation to do the multiplication. And then in addition, there's also a please evaluate the whole thing in just one go function, because for certain classes of vector fields, it's actually possible to do that more efficiently than each piece decomposed.
So you're just moving the evals that are required into the actual specification of the ODE. And then the solver is just
not quite, because this is something where let's pick a simple example. Let's pick something like Euler. If you're an ODE or Euler Mambayama, if you're doing an SDE, you write out the numerics for that. It's actually the exact same thing. It is vector fields times some increment in your control. And so if I just have an abstract notion of control, then I can now use the same Euler implementation, regardless of whether it's an ODE or SDE. Yeah. Cool. All right, so this is Diffrax, so this is differential equations. And I promised you not a long list of packages, so we're going to get them all done in one go. Lineax, it does linear solves, AX equals B. We have Optimistix, so this one does root finds. So in this case, we're doing minimization, root finding, fixed point least squares, non-linear least squares. Also, quick side note for anyone who's an optimization nerd, we also have the optimization theory going into this. With hybrid minimizer, and I'm saying things like, oh, I'm going to use like a BFGS approximation to a quadratic bowl, and then I'm going to go and do like a dogleg path down through that, but use transfusion to figure out how far down that path I should go. And we've got quite a nice way of decomposing these different pieces. So if you care about new optimization methods, then again, I think this is pretty cool. We've got things like quacks. This is actually multiple dispatch in JAX. We can do that too. And so this is a very, very simple example where my function, this could be any arbitrary function, but here's a very simple one, it's just one macro. And that macro is, please do not just an array, but in fact a LoRa direct approximation. That's familiar to people. I've seen just a couple of nods, but they're shaking with heads. This is a really popular way of doing fine-tuning deep learning models these days, where instead of you don't fine-tune your whole deep learning model, so you have some weight matrix somewhere. And instead of fine-tuning that whole thing, computing bits with respect to that whole thing, you replace that W with W plus A transpose B, where A and B give you some low rank addition to your matrix, and then you do this low rank adjustment to your matrix. And so this thing here, this is an implicit W, A, B as a pine tree. And when you interact with it, it feels like a W plus A transpose B. And then the way it feels like that is by saying, but please do multiple dispatch with respect to this splitting of little pieces. So we can do multiple dispatch in JAX as well. So the ... we have a slew of libraries, they do interesting things. And then also just jumping up the top, Jacobian linear operator, again, first class autodiff. If I want to define my A as Jacobian of some function, I can, and I don't need to write it explicitly. Let's move on to a case study. So case study, Diffrax versus a little scipy, right? You know, how does it compare to the granddaddy of them all in Python? First of all, Diffrax is much faster. A big part of this is, you know, scipy has routines written in Fortran, but ultimately it's calling your vector field written in Python. It's kind of slow. Also, autodiff support doesn't exist in scipy. GPU support, I don't know if you can get that through QPy. I suspect you probably can't. I'm not sure I'm going to debug that. And then in addition, loads more features, you know, FDEs, dead blah, 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 you know, the full gamut of things we like to have. What about Torch DPQ? Do people use Torch DPQ at all? So I'm seeing some sort of noodling of heads, people also. Mostly no, I think. So this for the longest time has been sort of classic like differential equation package written in Python for when you need autodiff. However, we're much faster because of all that stuff I talked about with JIT compilation earlier, right? PyTorch's compilation stack is kind of non-existent for models of this type. We have loads more features, and for bonus points, oh, I didn't actually include it here. I think I must have taken it out of this slide at some point, but for bonus points, we're also maintained, which Torch DPQ is not. And then, yes, what about Julia? How do we compare to Julia? So first of all, we are in Python. If you like Python, you know, that's useful. Besides that, we have a much better autodiff story. This is something where, you know, I should really qualify. Like, I'm actually not here to hate on Julia. I love Julia the language. Genuinely, I do. It is one of my favorite languages. It's so well designed. The problem is that the ecosystem on top of it is kind of like dodgy. In particular, there's still no strong autodiff story. If you want to do like higher order autodiff, you can kind of clutch this together, maybe, but not really. You know, go find a few help threads on the forums. And then like those things like auto parallel splitting across GPUs works very well for what we have, sort of ... I think it's a lot easier to just get over line with. Mostly with same speed. We're both JIT compiler, so no surprise there. And then with that, I do have a quick case study for you, which I think is probably, oh gosh, we are running rather late on time, aren't we? So I should probably get a mosey on. So okay, this is pretty much my last slide, I think. So okay, case study, gravitational waveform modeling. I don't pretend to understand the details of gravitational waveform modeling. I am merely the voice in which this is presented, and courtesy of Casey over in the Pathline for sending me this and sharing this with me. So this is something where, as I understand, you've got these two binary black hole system, and as they get closer and closer, and as they spin down together and eventually merge, you've got these kind of gravitational waves kind of like moseying off of one. And modeling the whole thing is hard, but modeling just this wave you see down at the bottom is apparently hard, but still easier. So you get pretty pictures that look like this, describing how does this thing evolve as those two black holes orbit each other. And then how they use Equinox, why I thought this was super cool. Using ensembling to take advantage of GPUs And so this was awesome. They had their previous best implementation was written in NumPy, actually. And it was smart. It was doing everything you could do with NumPy, but it was still NumPy. And so when you ditch that and move to something like a GPU, then you see these like dramatic 100% speed ups, not just because you're on a GPU. It was a very embarrassingly parallel problem. And then you start moving on like even larger, fancier GPUs, and you get another sort of 2 to 4 times speed up again. So do I have? Maybe I didn't write the line on here. He had a nice line for me, something to the effect of like, it used to take 2 weeks and now it takes us 2 hours. Right? Which, is wonderful, because I spend all this time writing a lot of the code that sort of, does abstract differential equation nonsense, right? And then at some point, someone later tells me, by the way, guess what? And that is hugely validating that this is possible, right? That this happens.
You have the reference for that?
For this, so I think the code for this one, he's got it here. For what it's worth, I think some of this stuff is still unreleased. So he said, I can talk about it, there's no problem. But I think if you want like a paper to go and read, I would just say email him and probably he can let you know. And there's one of the things they're using here, they've got Lineax. Oh, what do you know? Here we go. Yes, I did that. In fact, it's not hours, so it's minutes. But yes, wonderful stuff. So this is kind of cool. I think with that brings us to the end of the talk. So thank you so much for your attention. You've been a wonderful audience. I'll take any questions now. If you will have any questions later, please feel free to reach out to me. And then if you want some links to go and sort of like look up all of this, I've shown them up there too. We can probably share the slides or something too if you'll be able to click those things too. So I guess I'll pause for questions now, and then depending how brave we're feeling, I can go and jump into a collab and we can try playing on some stuff ourselves as well. Thank you.
So, I'm a convert, by the way. I'm totally into JAX. I'm writing an entire digital twin of an instrument we're building here in JAX. So totally into it. Love NumPyro. One thing I'm finding though is that JAX is becoming now so popular. There are lots of packages being developed that are doing very similar things. Like for instance, you had a linear solver earlier, right? But then you also have like the NumPy functions that do
the built-in
right?
ones, yeah.
So how do you? What's your opinion on how to navigate that environment, right?
Yeah. So in terms of the NumPy ones, actually the stuff in Lineax will often shell out into that where appropriate. We also have our own implementations where that's not available, but we will use the built-in ones if they're there. So speaking specifically to that, Lineax is there to provide a slightly higher level interface where you can more easily substitute out solvers or substitute in like Jacobian linear operators without having to figure out the details of, I don't know, materializing that or doing like a matrix-free method or something like this. Like it can handle all that for you. In terms of like how do you navigate the space in general, my very short answer is click on the Equinox link, scroll down to the bottom, and then I have a little ecosystem list, basically of packages that I personally can say, yes, I like those. And that gives you at least some measure of those are the ones worth using. I think this is kind of true of every sort of thing that gains a certain amount of popularity, right? Is that everyone comes in and writes their own package, and how do you figure out which are the ones that are still going to be here 2 years from now, right? Yeah. I don't have a better answer for you than sort of like squint at the GitHub stars and like try to figure out how maintained this thing is. Yeah.
Is there interaction between like for instance, Optax, right? Is this like amazing library that Google, like, are they ingesting some of the ideas that are coming out of the other packages into Optax, for instance, and making more of a unit like the optimization package in JAX?
Yeah. So I think the answer is mostly, speaking specifically to Optax, I think mostly no. Optax is basically the package for first order gradient optimization. And if you want to do that, go use that. If you want to do something else, like I don't like a root find Newton's method, blah, 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 then Optimistix, the one I discussed here. Side note, again, we don't reinvent the wheel. If you want to do first order gradient methods, Optimistix has a Optax minimizer class that you can use that will work with that, so that you can interop with these things cleanly. I think the only other thing I'd mention is just like go and talk to the authors and figure out what their level of investment is in some of these things. I think this is just kind of true of open source in general, right? Like, if it's VC backed, it exists until the money runs out. If it's, hobbyist backed, it exists until the interest runs out. If it's Google backed, it exists until they kill it, yeah, that's just open source in general. There's nothing specific to JAX here. The only advice I'd give you is, look at the ecosystem list that I personally can say, I like this.
It's very sad when you see data, for instance, in my example, right, which are at JAX library, but yeah, the last change was made years ago, right? And it's like,
Mhm.
an alternative, which PyTorch always has a well-maintained, up-to-date library, right? It's
Yeah.
like,
Yeah, this
this
is,
is what you do, right?
yeah. I mean, yeah, I guess that's kind of my role in all of this, right, is trying to provide some of the longer term maintained ones. It's actually something where I'm conscious of which packages I choose to create, because, you know, like, so you touched on like Giraffe, for example, I don't really do GNNs, right? It doesn't make sense for me to go make that because I can't promise to keep that alive. The other stuff I do if I can, because I actually use this data and I like this, right? Shrug. I don't have a better answer for you. Any other questions?
No.
I guess the only other comment I might make is that there's nothing specific to Jax here. This is true in PyTorch as well. Like Torch PPT was there until it wasn't, right? You know, etc.
Okay, let's see if there's anything on
Any questions online? But we'll stay around, we'll have some sandwiches and then we can do are people interested? Are you still
I'm
not
happy,
too
I'm happy
tired?
to.
Okay, so let's thank Patrick again.